Hi guys, Audrey here. So now we're going to do an example of a telescoping series. Okay, so aside from the fact that it says telescoping series right up there, there are two clues here that this is a telescoping series. The first clue is that it asks me to find the sum. And if you'll recall, we can really only easily find the sum of two different types of series because there are only two different types of series for which we could find the general term for the sequence of partial sums. Those series were geometric series and telescoping series. Now this is clearly not geometric because geometric is a number to the power of n. These are n's to the power of numbers, plus there are like plus signs and there's constants, and well, the constants don't really matter, but like this is clearly not a geometric series. So the fact that we're asked to find the sum in the case that it converges indicates that this might be telescoping. Now, the second indication here is that we have what looks like a rational function, even though this isn't a function because it's a series, but we have what looks like a rational function, and the denominator here, this can be factored. So what that means is it's possible we're going to be able to do a partial fractions decomposition to turn this into a subtraction. So that's really going to be our first step of this problem, is to take this thing right here, 2 over n squared plus 4n plus 3, and see if we can turn it into a subtraction. So 2 over n squared plus 4n plus 3. We're going to follow our steps for partial fractions. When we have a rational function, first we ask ourselves if we need to divide. The degree of the numerator is 0 because it's just a constant. The degree of the denominator is 2. So the degree of the numerator is less than the degree of the denominator. No division is necessary. So then our next step is to factor the denominator. N squared plus 4n plus 3 is equal to n plus 3 times n plus 1. Now we're going to create our partial fractions decomposition. So 2 over n plus 3 times n plus 1. These are both linear factors. They both only occur one time. So that means I'm going to separate it into two fractions with just a constant on top. So each factor of the denominator gets its own fraction, and they're linear, so there's just a constant on top. Now we take both sides of this and multiply by the original denominator. So that we can now solve for the numerators. We end up with 2 is equal to a times n plus 1 plus b times n plus 3. Now my zeros of the denominator are going to be n is equal to -3. So first I'm going to plug that in, and I will get 2 is equal to a times -3 plus 1, that's -2, plus b times 0, which gives me a is equal to -1. Next, I will plug in the second 0 of my denominator, which is n is equal to -1. And this will give me 2 is equal to a, -1 plus 1, so that's a times 0, plus b, -1 plus 3, that's 2, giving me that b is equal to 1. Okay, so now we've solved for our numerators. So we can say then that that original sum, n equals 2 to infinity, of 2 over n squared plus 4n plus 3 is equal to n equals 2 to infinity of -1 over n plus 3 plus 1 over n plus 1. Now I'm going to do something a little bit interesting here. Having the negative first sometimes makes the problem a little bit more challenging. It's useful to think of telescoping series is a sub n minus b sub n, where we're subtracting the second thing. Of course, it's totally doable if we leave it that way, but I'm going to switch it. So in other words, I'm going to look at the series n equals 2 to infinity, 1 over n plus 1 minus 1 over n plus 3. Okay, so now that was my first step. Write the thing as a subtraction. We wrote it as a subtraction. Our next step now is to find the general term of the sequence of partial sums. So that means I'm looking for S sub n. I'm going to make that a capital N this time. So we'll have n equals 2 to capital N, 1 over n plus 1 minus 1 over n plus 3 equals. Now, the first thing that we need to note when we're expanding this is that this thing starts at 2. It does not start at 1. So that means when I'm plugging things in, I'm starting with n is equal to 2. And when I plug in n equals 2, I get 1 over 2 plus 1, that's 1 over 3, minus 2 plus 3, that's 1 over 5. Plus, then I'm going to plug in 3. So then I get 1 over 4 minus 1 over 6. Now remember, we want to expand in the beginning until we find a pattern of cancellation. In other words, until we are able to cancel something out and see how those things are canceling out. So at this point, I've plugged in 2 and 3, and nothing has canceled out, which means that I'm going to now have to plug in 4. So when I plug in 4, I get 1 over 5 minus 1 over 7. And now we'll notice that that negative 1 over 5 cancels out with the positive 1 over 5. So we've kind of found our pattern of cancellation here. We're starting with negative. We're starting with negative. Then we're skipping 2 terms. And then we're canceling a positive. Okay, so now that we've figured out what our pattern of cancellation is, we can go to the end and cancel things out at the end as well, and plug things in at the end to see what's left over. That said, in order to find this pattern of cancellation, we started with 3 things in the beginning. It took us 3 expansions. So what that means is at the end as well, I'm going to want to write the same number of things. I'm going to be writing 3 things here. Okay, and I know that the last thing I'm plugging in is that number on top there. So the last thing I'm plugging in is that capital N. So the number right before that will come from just subtracting 1. So I'm going to be plugging in n minus 1 and n minus 2. Okay, so when I plug in n minus 2, I'm going to get n minus 2 plus 1. So that gives me 1 over n minus 1 minus n minus 2 plus 3. That gives me 1 over n plus 1. Plug in n minus 1. N minus 1 plus 1, that's just 1 over n. Minus, plug in n minus 1 to n plus 3. N minus 1 plus 3, that's 1 over n plus 2. Then I'm plugging in n, and nothing is going to change here. So I'll have 1 over n plus 1 minus 1 over n plus 3. Now, we can see that there are certain things that easily cancel out at the end. That minus 1 over n plus 1, we have right there. I'm going to skip 2 terms and cancel out the positive next to it. So I have my n plus 1 over minus 1 over n plus 1. I skip 2 terms, and then I canceled. Same up here. I had my negative 1 over 5. I skipped 2 terms, and then I canceled. Okay, so now basically we know that if I were to continue expanding negative 1, if I were to plug in 5, for example, the next thing that I got would be negative 1 over 6. So I know that that negative 1 over 6 is going to cancel out. If I kept going, I would then get a positive 1 over 7. So I know that the negative 1 over 7 is going to cancel out. So it's easy to see in the beginning what cancels out. To help us see what we need to cancel out in the end, we now want to use our pattern of cancellation to cancel the end out with the beginning. So in other words, we're going to pretend that that plus dot 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 is not there. And we're going to start with this negative 1 over 6. And we're going to skip two things. So I'm skipping the 1 over 5. I'm skipping the negative 1 over 7. If I pretend this is not there, the next thing I see is 1 over n minus 1. So that's the thing that I'm going to cancel with the negative 1 over 6. So it's kind of like if that n minus 2 had actually been 5, well, the negative 1 over 6 would have canceled with that 1 over n minus 1. Okay, so now we're going to move on to our next negative. Our next negative is that negative 1 over 7. So that's where we start. I start there. I pretend that's not there. I'm going to skip the 1 over n minus 1, skip the 1 over n plus 1, and then I'm going to cancel. So that negative 1 over 7 is canceling out with the 1 over n. If I were to keep doing this, my next negative would be negative 1 over n plus 2. My next negative that's not canceled. So then I would skip 2, except when I get to the thing I want to cancel, there's nothing there. So what that means is I'm going to keep the negative 1 over n plus 2. So I've canceled out everything I need to cancel. I have 2 terms left in the beginning. I've also got 2 terms left at the end. So we should always have the same number of terms left at the end as we have at the beginning. And now we have our s sub n. So s sub n is equal to 1 over 3 plus 1 over 4 minus 1 over n plus 2 minus 1 over n plus 3. And this is the general term for the sequence of partial sums. And this is useful because I know that the sequence of partial sums and the series are doing the same thing. So what that means is now I can evaluate the limit as n approaches infinity of s sub n, limit as n approaches infinity of 1/3 plus 1/4 minus 1 over n plus 2 minus 1 over n plus 3. And I get that this is going to 1 over 3 plus 1 over 4. Well, this right here is like 1 over infinity. This is also 1 over infinity. And we know that 1 over infinity, that bottom is getting really, really big, is going to 0. So this is like plus 0 plus 0. So this gives me 7 over 12. So then my final answer is that 7 over 12. In other words, we can conclude that our original series, n is equal to 2 to infinity, 2 over n squared plus 4n plus 3, converges to 7/12. And that is all. That is our answer. If I had gotten an infinity or it does not exist for that limit, the answer would have been diverges. We're done. Bye, guys.